Okay, so here's Vera Virtual, and if you open a terminal, it's the little black icon down here. If you hover the mouse over it, it says terminal, use the command line. Okay, now if you open this up, you'll just see a black screen, and this is called a prompt. This little Vera Virtual colon $sign, and you can type commands here. And one of the commands you can type is ls, and ls is list the files in the current directory. And all we have here are, you might have some other files if you've used Vera Virtual for other purposes, but you should have a program over here, cprog. Now I know some of you have Vera Virtual 3, and so things may look a little bit different. Hopefully you have a cprog directory over here, an LC3 compiler directory over here, so everything will be set up for you. And also. And so now, if this is the directory we're interested in, C programs. So you go C prog, CD, C prog. You have to spell the name correctly. CD is change directory. So a directory is like a folder, but on the command line, you think of them as directories because they're listings. So then you can see that we're in the cprog directory. If you look at it on the desktop here, when you open a terminal, you're in your home folder. Now here's your home folder here. Is if I open this, you can see the folders here, the same folders as the names in this listing, cprog desktop. These are all directories, okay? So then if you double click here, you'll see the file and a directory in cprog. And if I want to say the same information here, I type ls, and I can see the same name, hello.c, makefile, stdio.h, and text. Now, you can look at these if you wish, but the text ones are the programs that go with the text, and they're fancy in the sense that they do nice things. They're what you'd expect of C programs if you were just learning C by itself. And so, but I put them in here sort of to get them out of the way so it doesn't look overwhelming. Now, if you have Vera Virtual 3, you likely don't have this. You likely have a whole mess of these files, like figure whatever from the text. So you'll just have to ignore those for now. And you may not have the hello.c program, or you may have a different one. Well, this is a first C program, but we're not going to. And let me show you that. You use text editors, right? The text editor, built-in text editor here on Vera Virtual, which is Linux Mint, is called Xed for editor. Okay, so if I do that, then I end up with a simple C program. Okay, but we're going to start even with simpler programs. But let me just tell you what a C program is. So a C program here is a list of functions. Now, execution of the program always starts with the main function. Now, this should remind you of you all having taken Java, that Java also begins with the main method in a particular class. And that main method has a different header. It doesn't have a return type. And instead of void here, it has like int argc, comma, argv square, or string square bracket, something like that. And so it's going to have sort of a different header than we have, and that's frozen. Now, but it's the same idea. Execution starts with the main function. In Java, it's called a method, but methods in Java are functions in C. Functions don't occur inside classes. C doesn't have classes or objects. In that sense, it's simpler. It just has, from your point of view, from the point of view of someone coming from Java, it's like it just has methods with no surrounding classes. Okay, and you can see that this program should, if I compile it, just translate it to machine language, just should print hello LC3 from this printf statement. Now I can compile this directly into, let me open another terminal and do that in a different terminal. this will also repeat these instructions. If you want to see where you are, you can type ls, type cd, cprog, then ls, and then you have here, um, you can compile it directly. This is the way in CS212 we do it. We have the GNU compiler connection. That's GCC, hello.c, and then you do dash O for output, and that's the executable name, hello. You do that and you look and you see you have a new green name, hello. That the coloring is white is just normal text files. Blue is a directory. Um, green is an executable. Then if I do specify in the current directory, execute the file, that's what the dot slash is. Look in the current directory, find the executable hello and execute it. And there you see it. Hello, hello LC3. And you see that I haven't put in this is the analog in Java of system.out.println. There actually is a printf function. You can do system.out.printf in Java, and so you could actually do the analog of that here. So this is like your hello world program in Java, your hello world program in C, and it just is there to show you how to compile and run a program. Well, that's not what we're going to do. I just want to show you this because we are going to do something a little different. But let me stop here for a second and ask, does anyone have any questions?
When did you when was this Vera virtual version made?
In maybe in September. It's so um, if you don't, you want, have you, so what behind that question is likely the issue, you have some issues.
You gave it to me last semester, Vera virtual. So I don't know if do I have
Oh,
the same
well,
one?
did you log in with Vera 19?
Yes.
Then you should have the same version.
Okay.
Yes, it's only, and if you have this background, if you had an earlier version, you wouldn't have this blue background. You'd have like a meadow scene, I think, or something like that. So the backgrounds are different. You can tell if it's the background is mainly green, something like that, then you have Vera Virtual 3. And so if you have this blue background, then that's okay. That's going to be, you'll have the latest version. Okay. Yes, it's important to not also don't update or upgrade Oracle VirtualBox unless you have some kind of problems, but then you should probably talk to me first. You don't need to update Vera Virtual. Don't because everything works. If everything works, don't try to fix something because otherwise you're likely to break something. Usually those things can be fixed, but you just don't, you want to concentrate on the class and stuff like that, not on messing with, having screwed up your Vera Virtual installation. Also, sometimes Vera Virtual 4 opening on VirtualBox will at the beginning will hang. It will just give you a black screen when you first start it up. If that's the case, just close Vera Virtual Store and restart it. Sometimes it might require once or twice doing that. Once it gets started, then you can up here when you do close, select save computer state, not power off the machine. And then if everything's working fine, that will lead the next time when you open it to things to be okay. Okay, so let me, now, let's see if I go to, no, I didn't want that. I wanted to make this larger. And that did not seem to be happy. Okay. Okay, so let's just leave the windowing alone. I just wanted to have space for you could see this first thing is a directory. And I'm going to extract it here. You don't necessarily have to do this on Vera Virtual because what we have, yeah, in fact, you might not want to do that because what I have here is some PDFs and some files. Now, Oh, I didn't give you the C files. Oh, but they're in here. Like if I go to activation record 0, that's with 0 ASM. So let's look at this first one. Okay, so we are going to, there's something called the activation record, and here's our first program. And you can see it does nothing. It's even simpler than the other one. Now, let me show you, we need the context for what's happening in C. So when a C program runs, what was the problem? The problem for C was developed when there were no functions. So it was the first programming language to have functions. And the problem was that basically, how can one function call another function? Now, the solution to that problem is to make a and to also to name variables. Like if I want to perform C in the code something like this, which is a Java and a C instruction, the programmer can use any name they want. The compiler has to be able to translate this to assembly language without using these names, because it doesn't know what it can't. It doesn't reference the names in the program. So what it does is it makes a format for every function. And so the format has a standard form in which there's going to be what's called a stack. That's not a very good base for a stack. Let's get one that's a little bit less wavy. Okay, so here is the base. This is like we would put a -1 or a 0 here. This is the base of a stack. And it's a stack of frames. Each frame corresponds to a function. So when the LC3 starts, it sort of wants to call the function or execute the function. Calling a function, the word call is the same, means the same thing as start executing the function, or starting to carry out the instructions in the body of the function. So what it does is it makes a frame in memory here. It reserves a space according to a certain format. This is called, like the first function that runs is main. So this is the main function. This is the activation record. Of the main function. It's basically the space for all the variables and stuff like that. So it's got a fixed format. And we'll look at that in a second. So this is the solution to the problem of that it's going to name the variables and give memory slots for them in this space, and it'll have memory slots for all the information it needs to sort of disassemble the main call and go and sort of return at the end, because every function, you start executing it, you carry out the body of the instructions, then you return a value and stop execution of the function. Now, one thing that main could do is call other functions. If main calls another function, then what happens is that its task is put on hold. All its variables are saved here, just sort of frozen, and this would be say a function call, say F1, right? So this is the activation record for function F1. Okay, well, it has the same format here as this one. It might have more variables or fewer variables, because each frame has space for all the local variables. And if F1 called a function like F2, then F2's call frame we put on top here. This would be F2, this is the activation record for F2, okay? And what happens is that when F2 completes, at the bottom here, its first memory cell is going to be the return value that's going to be returned to F1. And the bottom down here is going to be the return value that will return to main. And main also has a return value that it returns to the LC3. Now the LC3 doesn't do anything with it because it's not really an operating system. If on the real on the real sort of operating system like Linux, the shell will be calling it rather than the bare machine, and so it would do something with this return value, and I can show you that. But the idea here is then that so you make this stack where you main calls F1, F1 calls F2, and then it sets the whole effect of F2, apart from printing everything to the screen, is to make a return value. And then this whole frame is popped off the top of the stack, and everything is set up for F1 to continue executing with this new value that it's had there. And then once it completes its task, it's popped off the top of the stack, leaving just the return value that gets returned, and main starts running. And then when main completes, it finishes with its return value and the program's over, or the execution of the program is over. So understanding these activation records is the key to understanding how everything works. So let's look at an activation record. We'll come back to this, but this is sort of the minimal activation record. This is the activation record for main, for this program here. So it has no local variables, and we're going to go and slowly build this up and understand what's going on. So let's look at that activation record. You can see that the base of the stack is at cell EFFF. It's as if the program wants to leave as much space as possible in case the program is going to be so gigantic it's going to use all 65,000 memory cells. So just to not have any limits, it gives the program as much space as possible. So it goes way to the bottom. You know, if I added one here, there's a little space at the bottom for extra stuff, but it starts way at the bottom at EFFF. And this is the location, all the registers. Now, let me see, what are the ones that are special? Well, it turns out in this case, for activation records, R4 is going to be special. R5 is going to be special. R6 is going to be special. R7 is special. And of course, R0 is special. So that only leaves R1, R2, and R3 as general purpose registers. Now, it will save sometimes like R7 because R7 is saved. So it can also use R7, but otherwise, you don't have many registers. So the whole focus shifts from using registers to using memory cells. Okay, let me take a moment here.